Welcome students. In this class we are starting a new topic called successive differentiation. Now what is the meaning of successive differentiation? Now if we are given, say, y is equal to x squared and we are expected to find dy over dx. So dy over dx, foremost, what exactly is dy over dx? It is nothing but differentiation with respect to x. The independent variable is x and the dependent variable is y. So any change in x will be reflected in y. So if we were to find dy over dx, we would foremost get 2x. Now this is called as the first differentiation. Or it can also be called as the first derivative, or it can also be called as the first change. So there are three different ways by which you can address. Now just as we have the option of addressing this particular expression in three different ways, we also have the option of representing this expression in three different ways. So instead of saying dy over dx, I can simply state here y dash is equal to 2x, or I can simply state here f dash is equal to 2x, or we can simply state here y1 is equal to 2x. So having given this representation, we can also go forward to obtain the second differentiation. So let me just draw a line here and show you what is the second differentiation will look like. Now we got dy over dx and someone is asking us to obtain the second derivative of this. In that case, what are we to do is to operate on dy over dx by d over dx. Now d over dx is a differential operator. The meaning is this operator is operating on the left hand side as well as it is operating on the right hand side. So when it operates on the left hand side, we would get d squared y over dx squared, and on the right hand side when it operates, differentiation of 2x would give me 2 times of differential of x is going to be 1, so that's simply going to be 2. So this is the second differentiation. You can simply state here second differentiation of y. We can either represent it like this or we can represent it like this, y double dash is equal to 2, or we can represent it like this, f double dash is equal to 2. Sometimes we can also, in some cases, the representation will also be like this, y2 suffix 2 is equal to the value. So what have we done here? We have successively performed a differentiation, the first differentiation, the second differentiation. We can move on with the third differentiation if there were to be independent variable x, but in this case it's a constant, so the third derivative would result in 0. So this is the exact essence of successive differentiation. So having got that out of the way, let us have a few concepts that we need to know. So these are some concepts. Now if you are finding dy over dx, and if you want to represent dy over dx in a different fashion, say for example in this case we just have dy over dx, but what if you wanted to rewrite this as 1 over dx over dy? Is it possible? Can you do this? Let us actually try this. If dy over dx is equal to 1 over dx over dy, Now I'm going to demonstrate that dy over dx is indeed equal to 1 over dx over dy. Now please bear in mind, when I state dy over dx, the meaning is I'm performing the operation on y using the differential operator d over dx. Similarly, when I state dx over dy, I am performing the differential operation onto x using the operator d over dy. Now, it is imperative to understand d over dy and d over dx are totally different operations. So have that in mind. So there is no way of hard and fast rule to outrightly state that these two are going to be equal. Of course, in this state, or I would say to begin with, the first differentiation, dy over dx is indeed equal to 1 over dx over dy. Now why did I make that statement? Because more so often people tend to assume that d squared y over dx squared will also be equal to 1 over d squared x over dy squared. This is not going to be true. This is absolutely a false relation. So the point I wish to make here is, however, though in this case the first law is going to be true, the second law will always fail. So that is the important point I wish to bring to your attention, that whenever we state dy over dx, we are operating on y with the operator d over dx. Similarly, when we state dx over dy, we are operating on x with the operator d over dy. And d over dx is totally different from d over dy. They are two different operators. So though in spite of d over dx and d over dy are being two different operators, yet the first relationship is true, whereas the second relationship is false. You will not have equivalence, but in this case they are not equal. So since they are not equal, this is actually a true relationship. So the take home point is d squared y over dx squared is not equal to 1 over d squared x over dy squared. So that is an important point. Okay, so having mentioned this, let us see if the first relationship is true. Now if you remember, I have taken y to be equal to x squared, right? And then I went on to find dy over dx to be equal to 2 times x. So this is the first state. Now I want to find out dx over dy. So that is why I stated d over dy is totally a different operator from d over dx. So now to obtain dx over dy, we will have to rewire this equation. Now I've got y is equal to x squared. So from here, if I were to take the square root on both sides, this is going to give me root of y is equal to x. So therefore we have x to be equal to root of y. So this is now our new equation. Now over here we are not going to be differentiating with respect to x, but we are going to be differentiating with respect to y. So when we do that, we would get on the left hand side dx over dy. On the right hand side, this is actually y raised to the power of 1 over 2. So when you differentiate y raised to the power of 1 over 2, this is going to be 1 over 2 times y raised to the power of 1 over 2 negative 1 times differentiation of y, which is going to be 1. So this can be rewritten as 1 over 2 times y raised to the power of negative 1 over 2, which can be rewritten as 1 over 2 times, I can bring this down, so I get y raised to the power of 1 over 2, which is nothing but 1 over 2 times root of y. Now what is root of y? Root of y is nothing but x. So this is rewritten as 1 over 2 times x. So what is this? This is nothing but my dx over dy. Now we got this dx over dy, and then we have this dy over dx. So according to our first property, dy over dx is equal to 1 over dx over dy. So let us see that. Okay, testing the property, testing the law. So what is the law? The law states that dy over dx is indeed equal to 1 over dx over dy. Are they equal? So let us try them out. So dy over dx, I'm going to substitute, that's going to be 2x, and in this case it's going to be 1 over dx over dy is 1 over 2x. So if you were to flip it, you get 2x. So this would mean the left hand side is indeed equal to right hand side. So that is a wonderful way that we have got. So now the next point comes, as I mentioned to you, I'm going to find out if d squared y over dx squared is equal to 1 over d squared x over dy squared. I'm going to show you whether this property really holds good. So let us do that. So as I mentioned to you, we've got two things. So the first differentiation for this dy over dx is 2 times x, and the first differentiation for dx over dy is 1 over 2 times y, root of y. So let me write that, root of y. So now I'm going to perform the second differentiation. So d over dx of dy over dx is equal to d over dx of 2x. This is going to give me d squared y over dx squared. Differentiating of 2x again would give me 2. So this is fine, I've got this. Now let us move on to this. I'm operating on with d over dy onto dx over dy. This is going to be the operation d over dy of 1 over 2 times root of y. Probably I can rewrite this as d over dy 1 over 2 times y raised to the power of 1 over 2. If I were to rewrite this further, probably I can take 1 over 2 out. So d over dy of, I can push this y raised to the power of 1 over 2 to the numerator. It's going to be y raised to the power of negative 1 over 2. Now I will differentiate it with reference to y. So this is going to give me negative 1 over 2 times y raised to the power of 1 over 2 negative 1, which is negative 1 over 4 times y raised to the power of negative 3 over 2. I can push it down. If I were to push it down, this is negative 1 over 4 times y raised to the power of negative 3 over 2. Now, how do I rewrite negative? In fact, it will be positive 3 over 2 because it's already negative here. So, I'm going to rewrite y raised to the power of 3 over 2 in this fashion. So, y raised to the power of 1 over 2 raised to the power of 3. Right? So, I can very well do that, right? Because of the law of indices, a raised to the power of m raised to the power of n is equal to a raised to the power of m times n. Right? So by this property, what I can do is I can very well make that representation. But y raised to the power of 1 over 2, as I mentioned to you, we have taken, now let me write that down. Now since root of y is equal to x, which means x is equal to y raised to the power of 1 over 2. This is nothing but 1 over 4. Of course, there's a negative sign there. 1 over, in place of y raised to the power of 1 over 2, I can substitute x. You got x cubed here. So you have got negative 1 over 4, 4 times x cubed. So this is what? This is d squared x over dy squared. This is what we have got. Now the question is, what is the most important question that we are seeking to answer? The law is d squared y over dx squared is d squared y over dx squared equal to 1 over d squared x over dy squared. Is it true? So what is d squared y over dx squared? It's over here, the value is here 2 is equal to 1 over d squared x over dy squared. What is it? That's nothing but negative 1 over 4 times x cubed. So when you flip it, you get 2 is equal to 4 times x cubed with a negative sign. Are they equal? Are they equal? The question is no. Right? So clearly I have just shown you these two results, that this is not equal while the former case holds good. So having established these two very important results, we will move on, students, to do other questions. Students, we have a beautiful question. The question wants us to find out what exactly is d squared x over dy squared. Now we have four options. Now just make an observation on to the option number D that has been given. So we got d squared y over dx squared raised to the power of -1. Now what exactly is this? Now if you were to rewrite or give the representation for d squared x over dy squared as 1 over d squared y over dx squared, this is nothing but d squared y over dx squared raised to the power of -1. So this is exactly what they have written there. They are telling you that d squared x over dy squared is nothing but, d squared x over dy squared is nothing but d squared y over dx squared raised to the power of -1. Is it true? Of course it is not true, because we just did a study that d squared x over dy squared is not equal to 1 over d squared y over dx squared or d squared y over dx squared raised to the power of -1. So clearly we cannot, or we should just ignore option D. Option D is not in the race. Now, having mentioned that, we have three options, 1, 2 and 3, or A, B and C. So we will have to make our choice from that. So to begin with, let us consider d squared x over dy squared. I'm going to rewrite this as d over dy of dx over dy. Now clearly we know that, what do we know? We know that dx over dy can be rewritten as 1 over dy over dx. This has been found to be true. Or I can further rewrite this as dy over dx raised to the power of -1. Now what exactly is happening here? We are actually differentiating y with reference to d over dx. So the underlining point is always y is a function of x. So if you were to find dy over dx, you will subsequently get another function of x. You can verify this. Say for example, if I were to take y is equal to x raised to the power of 4, and if you were to differentiate this, you are going to get 4 times x raised to the power of 3. This is a function of x. So why am I telling you all this? For the simple reason that dy over dx will be a function of x. Now why is this so important to us? Of course it is very important to us because of the fact that we are going to be replacing dx over dy as dy over dx raised to the power of -1. And what we have got exactly here? We have d over dy of dy over dx raised to the power of -1. So we have a differentiation present inside, and that is raised to the power of -1, and we are to operate it with d over dy. Now we are going to adopt a certain trick from mathematics. What is the trick? Clearly we know that this is a function of x, so I would be more happy to differentiate this with reference to x. So to get that, what I'm going to do, I'm going to just place in fact I'm just placing a dx here, and then I would just place dy over dx raised to the power of -1. So clearly what is happening here, this quantity which I have just shown you to be a function of x would have to be differentiated with d over dx. That's perfectly fine with me. So since I placed a dx here, I will have to neutralize it with presenting a dx there, and then after neutralizing this dx, I've got a dy there. So all I need to do is just simply place the dy there. So I'm not doing any additional augmentation to the given expression. Nothing. All I'm doing is to rewrite this in this fashion. So let us now differentiate dy over dx raised to the power of -1. Now we are going to follow the same differentiation sets or skill sets that we were exposed to. If you are given y is equal to x raised to the power of 4, you were to differentiate that, you are going to get 4 times x raised to the power of 3. So that means the power becomes reduced. That's exactly what we are going to do here. So differentiating this would give us -1 times dy over dx. Now once the quantity comes down, there is a diminishing in the power. So -1 with another -1, that's fine, times I need to obtain the differentiation of this quantity, dy over dx, alright, followed by there is a dx over dy. So that is exactly what we have to do here. Now this can be rewritten as negative times, in fact -1 times this quantity would result in a negative sign, so let that be there. So this is going to be dy over dx. -1 is going to be -2. Now I already explained to you what happens when you use the operator d over dx onto a quantity like this, dy over dx. So in this case, this is going to become d squared y over dx squared, simple as that, and close the parenthesis. So now you have got dx over dy. Now we need to do something now, because dx over dy is here, but we have got dy over dx, so we have to again rewire certain components. So in this case we are going to rewire this. So now we have got negative dy over dx raised to the power of -2 times d squared y over dx squared, right, times dx over dy. Now dx over dy, I can rewrite it as dy over dx raised to the power of -1. Why am I able to do that? For the simple fact that dx over dy is nothing but dy over dx raised to the power of -1. So we've already got that. Now I can club these two together. If I were to club these two together, this is going to give me negative dy over dx raised to the power of -3 times d squared y over dx squared. So this is a beautiful result. Now the question comes, which of these following options would be the right one? So we got option A, option B, option C. So we need to have a negative sign, and we need to have dy over dx raised to the power of -3. So we got dy over dx raised to the power of -3, a negative sign, but we don't have a negative exponent here. We do not have a negative exponent here. So option C is the best option that has to be selected here. So this is a beautiful question, because of the very fact that given a d squared x over dy squared, we are able to rewrite it as negative dy over dx raised to the power of -3 times d squared y over dx squared. So that is a marvelous representation for a double differential operation. So students, we will go on to the next question. Students, we are given this question: if y is equal to sine of sine x, then we are expected to prove that y2 positive tan x times y1 positive y times cos squared x is equal to 0. So foremost, let me just start off by writing, consider the given question, y is equal to sine of sine x. Now I would be performing the differentiation because I need to extract, or in other words, I need to go up until y2. So that would mean I need to get y1. So y1, differentiating this with respect to x, we get. So what do we get when you differentiate this? This is entire term. So this is going to be cos of sine x times, you will have to differentiate sine x. So differentiation of sine x would give us cos x. So this is what you have got. So you got two quantities here. So this is one quantity, and then you got the next quantity. So this is my u, and this is my v. So to get y2, you will have to use product rule. So d of u times v is equal to u times v dash positive v times u dash. So therefore y2 is equal to cos of sin x, this is my u, differentiation of cos x would give me negative sin x positive cos x times differentiation of this quantity, that's going to give me negative sine of sin x times differentiation of sin x, that's going to give me cos x. So after you have got this, you will have to adopt the concept of backward substitution. In other words, rewrite these components using y1 and y. Now we have got cos of sin x, right? But I also see cos of sin x. So if I were to take this as 1, if I were to take this as 2, take this as 3, from 2 we have, so what do we have from 2? So you got y1 is equal to cos of sin x times cos x. So from here, if I were to extract cos of sin x, I would get cos of sin x to be equal to y1 over cos x. So this is what I am getting. So what I'm going to do, I'm going to take this and I'm going to place it here. So that's for one side. The next part is sine of sin x. So what is sine of sin x? It's y. So let us rewrite those things. So therefore 3 can be rewritten as y2 is equal to y1 of cos x. There is a sin x and a negative sine, that's fine, positive cos of sine of sin x, that's going to be y, there's a negative sign, so it's going to be negative y times cos x and cos x, that can be multiplied. So this is going to be cos x, right? Cos x and cos x, they can be multiplied, giving me cos squared x. So this expression is what we have got. Now we can further rewrite this as y2 is equal to negative sin x over cos x. What is that? That's tan x, right? So it's going to be y1 times tan x negative y times cos squared x. So this is what I've got. Now if I were to move everything to the left hand side, this would mean I would now have y2 plus y1 tan x plus y times cos squared x is equal to 0. So what is this? This is exactly what we wanted, right? See that? Same thing. So you can simply say hence proved. So this is a nice question, students. We can move on to the next one. Students, we are given this question: if y is equal to sine of 5 times sine inverse of x, and that we have 1 negative x squared times y3. y3 stands for the third derivative, and that is equal to lambda times x times y2, the second derivative, positive mu times y1, the first derivative. So this has to be achieved by us, given that the value for y, and from here we will have to extract lambda positive mu. So let's do this question. So foremost, what I would do is I would consider y to be equal to sine of 5 times sine inverse of x. Now this is a beautiful question, and it involves some tentative threading. So what I mean by that is that we need to be a little bit cautious in approaching this, because if you were to outrightly start differentiating this term first time, second time, third time, you will forever end up in obtaining the derivative. So there wouldn't be any termination at all. So hence it is imperative for us to adopt a way by which we can achieve the end result, lambda positive mu. So for that, foremost, let me just state here, differentiating with respect to x, we get, so this is going to be y1 is equal to, differential of sine would give us cos of 5 times sine inverse of x. Differentiation of sine inverse of x is going to be 1 over root of 1 negative x squared. So this is fair enough. Now with our quantity sine inverse of x, we also have a constant 5, so we will have to place that constant 5. So what I'm going to do is I'm just going to place 5 there, because we are differentiating the entire quantity 5 times sine inverse of x. Though we might be tempted to negate the constant or take the constant out, but it is not advisable to do that. So what we have got here, this is equal to cos of 5 times sine inverse of x times 5 over square root of 1 negative x squared, and that is equal to y1. So now what I'm going to do is I'm going to push this y1, in other words I'm going to push this root of 1 negative x squared to the left. So that's going to be y1 times square root of 1 negative x squared is equal to 5 times of cos of 5 times of sine inverse of x. Now what I'm going to do next is I'm going to take, let 5 times of sine inverse of x be equal to sum phi. So if I were to take this as 2, therefore I can rewrite 2 to be as y1 times root of 1 negative x squared is equal to 5 times cos of 5 times sine inverse of x is phi. So this is going to be cos phi. So probably it's better to write like this, cos phi. That's fine. So since I've taken 5 times sine inverse of x is equal to 5, you can see that the original equation, what is it given? I'm going to rewrite this over here. So given y is equal to sine of 5 times sine inverse of x. Now since 5 times sine inverse of x is equal to phi, hence I can now rewrite y to be as sine of phi, right? So that is a nice way that we have got our y. Now having obtained the y, let's go back to our system. So clearly we get y1 times root of 1 negative x squared is equal to 5 times cos phi. Now what I'm going to do is I'm going to rewrite this cos phi as square root of 1 negative sine squared phi. Now clearly we know that sine phi is y, so this is going to be 5 times root of 1 negative y squared. So from here this is going to be y1 times root of 1 negative x squared is equal to 5 times root of 1 negative y squared. So we have a beautiful system which is manageable. So now we will have to start off with our differentiation process. So before we could do that, clearly you can see that there is a presence of a square root there. I don't want to have that. So the best way, before we could start our differentiation, let us remove that. So I would be squaring both sides. So if I were to square both sides, this is going to be raised to the power of 2. This entire thing is raised to the power of 2. So this is going to give me y squared, y1 times 1 negative x squared, 5 squared, that's 25 times 1 negative y squared. So take some precaution when you're writing the indexes because we are using an index and a suffix, so those two things should not be mixed up. So now let us start our differentiation. So differentiating with respect to x, we get, so this is uv, so I will start by placing the u, so that's going to be y suffix 1 squared of differentiation of 1 negative x squared, that's going to be negative 2 times x, followed by differentiation of this quantity. So let me place the 1 negative x squared, and this is going to be 2 times y1 times differentiation of this y1, that's going to give me y2. Now this is equal to 25 times differentiation of 1 is 0, differentiation of negative y squared is going to be negative 2 times y times differentiation of y, that's going to be y1. So I have, clearly you can see that you have a 2 year, a 2 year, and a 2 year, so I can get rid of this 2, this 2, and this 2, and I have a y1 and a y1 and a y1, so I can get rid of that y1, y1, and y1. So what is left now? So I get a y1 now, of course there is a x there and there is a negative sign, fine, and followed by 1 negative x squared times y2 is equal to 25 times, you have a negative sign and a y. So this is the system that we have got. Now the first differentiation is finished, the second differentiation is finished, so we got y2, but we need to get y3. So differentiating with respect to x, we get, so we will have to differentiate this quantity. So in this case it's uv, so I'm going to take a negative sign out, so it's going to be y1, differentiation of x is 1, positive x times differentiation of this y1 would give me y2, so that's fair enough. This is uv, so it's going to be 1 negative x squared, differentiation of y2 is going to be y3, followed by y2 times differentiation of 1 is 0, negative x squared would give me negative 2x is equal to negative 25 times differentiation of y is going to be y1. So let us expand it and check out if anything can be cancelled. So this is going to be negative y1, negative x times y2, and positive 1 negative x squared y3, and this is negative 2 times x and y2 is equal to negative 25 times y1. Now negative 2 times x2, negative xy2, these two can be connected. So if I were to add them together, I would get negative 3 times x y2, and then I have y1 here, so let me place this, followed by 1 negative x squared times y3 is equal to negative 25 y1. So now we can actually club these two together, right? Negative 25 and negative y1. So what I'm going to do, I'm going to retain this 1 negative x squared times y3, and then I will place negative 3 times x y2. So now I'll push this to the other side. So negative 25 y1 positive y1, which is going to give me negative 24 y1, and I've got 1 negative x squared times y3. Now what I will do, I will also push this negative 3 times x y2 to the other side. So that would give me positive 3 times x y2. Now if you were to compare the system, so let's go back and compare it to the given system. On the left hand side, 1 negative x squared times y3. So you see here, on the left hand side, 1 negative x squared times y3. So that has to be followed with lambda times x into y2. So lambda times x into y2. So we got x into y2 here. So I'm going to rewrite it like this: 3 times x into y2, and followed by positive of negative 24 times y1, and this is 1 negative x squared times y3. So let me rewrite the problem down. The problem is given to be as 1 negative x squared times y3 is equal to lambda times x into y2 plus mu times y1, and then they want us to find the value of lambda positive mu, what exactly this would be. Now if you were to compare this, so this is the original system, I'm taking this to be say sum 4, comparing 4 with 1, we get, so what do we get when you compare 4 with 1? Clearly this would mean that lambda, or you can write it like this, lambda is equal to 3 and mu is equal to negative 24. So this is what we have got. So from here, what is lambda positive mu? So therefore lambda added with mu is equal to, lambda is 3 and mu is negative 24. So this is going to give me negative 21. So this is a beautiful question, and this is the right place for us to box the result. Students, we are given this question: if y is equal to a times cos of ln x positive b times sine of ln x, we are expected to prove x squared times y suffix 3 positive 3 times x y suffix 2 positive 2 times y1 is equal to 0. So foremost, let us start off by consider y to be equal to a times cos of ln x positive b times sine of ln x. Now we will have to perform the differentiation. So I'm going to state here, differentiating with respect to x, we get, so differential of y would give us y1. So this is a times differential of cos is going to be sine, of course there is a negative sign there, so it's going to be sine of ln x times differentiation of ln x, that's going to be 1 over x, positive b times differentiation of sine is going to be cos of ln x times differentiation of ln x is going to be x. Now what I wish to do is, I would like to take x out. So if I were to take x out, or the best way is multiplying both sides by x, we get. So when we do that, this is going to be y1 times x followed by negative a times sine of ln x positive b times cos of ln x, right? So now what I would do is, I would perform the differentiation again. So differentiating with respect to x, we get, so this is product form, so y1 times x, so this is going to be y1 times differentiation of x is 1, positive x times differentiation of y1 is going to be y2 is equal to negative a times differentiation of sine of ln x is going to be cos of ln x times differentiation of ln x, that's going to be x, positive b times differentiation of cos, that's going to be negative sine of ln x times differentiation of ln x is going to be x. So we have got a similar situation with x in the denominator, so I would be multiplying both sides by x, so we get, so this is going to be x times y1 positive x squared times y2 is equal to negative a times cos of ln x negative b times sine of ln x. Now I can clearly take the negative sign out. If I were to do that, this is going to be a times cos of ln x positive b times sine of ln x. Now what is this? A times cos of ln x positive b times sine of ln x. You see that original question? A times cos of ln x positive b times sine of ln x being equal to y. So I can substitute y there. So this is equal to x times y1 positive x2, in other words x squared times y2. So this is what I've got. So now what I'm going to do is I'm going to be differentiating this again. So differentiating with respect to x, we get. So this is going to be x times differential of y1 is going to be y2 positive y1 times differentiation of x is 1 positive x squared times differentiation of y2 is going to be y3 positive y2 times differentiation of x squared, that's going to be 2 times x. So on the right hand side, differentiation of negative y is going to be y1. So we got something that is really going on well. So let us check how it works out. So I'm going to push this negative y1 to the other side. If I were to do that, I will have a y1 and a y1. So it's going to be 2 times y1, and then I've got positive x squared y3, that's fine, and then 2 times x y2 and x y2. So these two things can be added. So that's going to give me 3 times x y2 is equal to 0. Now let's go and compare the given system to what is required. You see, this is what is required. X squared y3, 2 times y1, 2 times y1, and 3 times xy2, 3 times xy2, all of them added to 0, all of them added to 0, hence we can conclude the result is proved. Hence proved. So that's the good place for us to draw the red line. So we'll move on to the next question, students. Students, let's do this question. We have been given y is equal to a times cos inverse of x. We are expected to prove 1 negative x squared times y2 negative x times y1 negative a squared times y is equal to 0. So foremost, I'm going to consider y to be equal to, now now let's just take this as y is equal to e raised to the power of a times cos inverse of x. So let me just consider that y is equal, because if we were to take y is equal to a times cos inverse of x, that would be too simple. So this is going to be e raised to the power of a times cos inverse of x. Now what I would be doing is I would be differentiating with respect to x. So what would we get? This is going to be y1 is equal to, now differentiation of e raised to the power of x. Now suppose you got y is equal to e raised to the power of x, and if you want to find dy over dx, what is that? That's nothing but e raised to the power of x. So similarly, you will be getting here e raised to the power of a times cos inverse of x times differentiation of this entire quantity. So what is that? It's going to be a times cos inverse of x. So what do you get? This is equal to e raised to the power of a times cos inverse of x times differentiation of course a is a constant, so I can just take a out. I need to just differentiate cos inverse of x. That's going to be negative 1 over square root of 1 negative x squared. In the previous lecture I have already shown you how exactly cos inverse of x is differentiated and the relevant formula. So I can rewrite this as negative a times e times a times cos inverse of x divided by root of 1 negative x squared. So that's fair enough, right? So now an important observation. Let's go back to the question. What is the question? The question states y is equal to e raised to the power of a times cos inverse of x. So what do you have here? E raised to the power of a times cos inverse of x. So I'm going to rewrite this as y1 is equal to negative a times y divided by root of 1 negative x squared. Now I would be cross multiplying. So once I cross multiply, I would get y1 times root of 1 negative x squared is equal to negative a times y. Now as I mentioned to you, I don't want to have a square root here, so I would be squaring both sides. So if I were to square both sides, this is going to be a square and this is going to be a square. So this is going to give me y squared y1, or you can say y1 squared times 1 negative x squared is equal to a squared and y squared. So much so for the simplification after the first differentiation. Now what I'm going to do is I'm going to perform the second differentiation right over here. So now differentiating with respect to x we get. So let me just mark it with a red line. So now this is uv, right? So it's going to be y squared, in other words y1 squared. Now I need to differentiate 1, that's 0. Differentiation of x squared with a negative sign would give me negative 2 times x, followed by a positive sign and 1 negative x squared times differentiation of y1 squared. So that's going to be 2 times y1, and then that has to be followed with the differentiation of y1, and that would give me y2. And on the right hand side, this is equal to a squared is a constant, so we have to differentiate y squared. So that's going to be 2 times y times differentiation of y, that's going to be y1. So we got quite a sum here. Now the main thing is we will have to make the proof here. So that is critical. Now before we could make the proof here, we need to make an observation. Say y1, 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 it can be cancelled. y1 can be cancelled here, y1 can be cancelled here, and y1 can be cancelled. So what are we left with? We are left with a negative 2 times x and y1, positive 1 negative x squared times 2 times y2 is equal to 2 times y and a squared. This is what we have left with. So what I'm going to do is I'm going to make one more observation. See, I got a 2 here, a 2 here, a 2 here. So I can cancel this 2, and this 2. And then I need to bring this to the other side. So I will bring it to the left hand side and rewrite this as 1 negative x squared times y2 negative x into y1. So this is going to be negative if I were to bring it to the other side. Of course you can either write it as y times a squared or a squared times y. This is what is asked, and hence I'm writing it in this fashion. So comparing, you can clearly see you get 1 negative x squared times y2, 1 negative x squared times y2, negative x times y1, negative x times y1, negative a squared times y, negative a squared times y is equal to 0. So hence proved. So this is a good place for us to draw the red line, and this is a beautiful question. So we will move on to the next one. Students, we've got a beautiful question. Given that y raised to the power of 1 over m positive y raised to the power of negative 1 over m is equal to 2 times x, we are expected to prove x squared negative 1 times y3 positive 3 times x y2 positive 1 negative m squared times y1 is equal to 0. This is a very beautiful result that we have to achieve, and all that we have been given is y raised to the power of 1 over m positive y raised to the power of negative 1 over m is equal to 2x. So foremost, what we will do is we will start off by consider y raised to the power of 1 over m positive y raised to the power of negative 1 over m is equal to 2x. Next, we would be differentiating with respect to x. We get, so differentiation of y raised to the power of 1 over m is going to be 1 over m times y raised to the power of 1 over m negative 1 times differentiation of y, that's going to be y1 followed by a positive sign. Differentiating this would give me negative 1 over m times y raised to the power of negative 1 over m negative 1 times differentiation of y would give me y1 is equal to 2. Now what I wish to do is I would foremost like to take y1 out. So this is going to be 1 over m times y raised to the power of 1 over m negative 1 positive followed by negative 1 over m times y raised to the power of negative 1 over m negative 1 times y1 is equal to 2. Next, what I wish to do, I would like to move this y1 to the right hand side. So that would give me 1 over m times y raised to the power of 1 over m negative 1. Positive times negative is negative 1 over m times y raised to the power of negative 1 over m negative 1 is equal to 2 times y1. That's fair enough. Now next what I'm going to do is I'm going to take this 1 over m outside. So if I were to do that, I would get y raised to the power of 1 over m negative 1 negative y raised to the power of negative 1 over m negative 1 times 1 over m is equal to 2 times, or I should say 2 over y1. So now what I would do is I would push this m to the right hand side. So if I were to do that, this is going to be y raised to the power of 1 over m negative 1 negative y raised to the power of negative 1 over m negative 1 is equal to 2 times m over y1. Now next I would like to rewrite this as y raised to the power of 1 over m times y raised to the power of negative 1 followed by a negative sign y raised to the power of negative 1 over m times y raised to the power of negative 1 is equal to 2 times m over y1. Now what I wish to do is I would like to push this y raised to the power of negative 1 down. So this would give me y raised to the power of m divided by y negative y raised to the power of negative 1 over m divided by y is equal to 2 times m over y1. Now I would like to use this part of the space, so I would like to take 1 over y out. That would give me y raised to the power of 1 over m negative y raised to the power of negative 1 over m is equal to 2 times m over y1. Now I can push this y to the other side, so that would give me y raised to the power of 1 over m negative y raised to the power of negative 1 over m is equal to 2 times m times y divided by y1. So this is 2, and I'm going to take this to be as my original system 1. So fair enough. Now you would be tempted to obtain the second differential y2, because in this case we just differentiated one time, but we need to get up until y3. So we need differentiating the quantity the second time, and then that has to be followed by the differentiation of the entire quantity the third time. But we cannot, or I would say if we were to attempt differentiating this the second time, then we would be landing up ourselves with greater problem than we originally started with. So for that we will have to make a few alterations. So what are those alterations? So I'm going to take here, you see this y raised to the power of 1 over m. I'm going to state let alpha be equal to y raised to the power of 1 over m and beta be equal to y raised to the power of negative 1 over m. So this would mean alpha times beta is equal to y raised to the power of 1 over m times y raised to the power of negative 1 over m, which is equal to 1. So I got a value alpha beta is equal to 1. And then let me just go one step further. Also, alpha added with beta is equal to what? Alpha added with beta will be equal to 2x, right? Because alpha is this and beta is this. So we got this as 2x. Now the question comes, if alpha plus beta is equal to 2x, what is alpha minus beta to be equal to? So this would mean alpha minus beta. So what is alpha minus beta? This is alpha, this is beta. So this would mean alpha minus beta is equal to 2 times m times y divided by y1. So I got alpha plus beta and alpha minus beta. Now the question is, how are we going to connect these two quantities? The problem is solved if we can connect these two. And there comes to our help algebra. Now from algebra I can state that alpha minus beta raised to the power of 2 is equal to alpha plus beta raised to the power of 2 minus 4 times alpha beta. This is an algebraic identity which I'm using here. So simplifying, in other words substituting, so this is going to be 2 times m times y divided by y1 raised to the power of 2 is equal to 2 times x raised to the power of 2 negative 4 times alpha beta is 1. So this is going to be giving me 4 times x squared negative 4. That's fair enough. And then this is going to be giving me 4 times m squared y squared divided by y1 squared. Now we see a 4 here, a 4 here, a 4 here, so they can be cancelled. So this would now give me m squared y squared divided by y1 squared is equal to x squared negative 1. Now what I wish to do is, let me use this space here. I can rewrite this as m squared y squared is equal to y1 squared times x squared negative 1. So fair enough. So that's a nice way to get to the point. Now from here I can differentiate this the second time. So differentiating this with respect to x, we get, so what are the differentiation? So let me use this space here. This is a little bit larger in size. So m squared y squared. So m squared is a constant. I differentiate y squared is going to be 2 times y times differentiation of y, that's going to be y1, is equal to, I should differentiate this, so it's UV form, so y1 squared of differential of x squared, that's going to be 2 times x, positive x squared negative 1 times differentiation of this is going to be 2 times y1, differentiation of y1 would give me y2. So this is what I've got. If you want, you can rewrite this. So I'm going to rewrite this over here. So this would mean I get 2 times m squared times y times y1 is equal to 2 times x times y1 squared positive x squared negative 1 times 2 times y1 times y2. Okay, so now I can clearly get rid of the 2. I have a 2 here, I got a 2 here, I got a 2 here, and I can get rid of this y1 a y1 and a y1. So now it's coming out beautifully. So this is going to be m squared. So let me start from here. M squared and y, this y1 is already gone. So this is equal to x. I got a y1 there, and then x squared negative 1, and I have a y2 there. So now I will have to differentiate this again. So differentiating with respect to x, we get, so what do we get? This is m squared times differential of y is y1 is equal to UV formula, x times differential of y1 is y2 plus y1 times differential of x is 1, positive UV formula, x squared negative 1 times differentiation of y2 is going to be y3, positive y2 times differentiation of x squared is going to be 2 times x. So I need to rewrite this. I'm going to rewrite this starting with this term. So let me write that. So x squared negative 1 times y3, that's fine. And then I have a 2 times x y2. So let me just place that 2 times x y2. Is there anything I can do? Yes, there is an x y2 there. So I can add xy2 with 2 times xy2. That would give me 3 times xy2. Fair enough. And what else I can do? So there is a y1 here. So let me have that y1 and let me push this to the other end. So it's going to be negative m squared y1, right? So of course let me give an implied sign here and equate it to 0 on this end. So this can be further rewritten as x squared negative 1 times y3 positive 3 times x y2. I can take y1 out. If I were to do that, it's going to be 1 negative m squared times y1 is equal to 0. Now let us check with the original system what we were given. So you can see that clearly. X squared negative 1 times y3, x squared negative 1 times y3, so that check is fine, and we will have to go and check for the other quantity. So let me do that. So the other quantity is 3 times x y2, 3 times x y2, and 3 times x y2, check, and finally you got 1 negative m squared times y1, 1 negative m squared times y1. So hence we can state hence proved. This is a beautiful result, students. Thank you so much. We'll meet in the next class with a different topic.